Yeah, thanks, Martin. Thanks, all the organizers for having me again, and thanks IPAM for hosting us here. It's always a treat to come out here. So today I'm going to talk about some work that we're literally just wrapping up as I speak, and this has been keeping us busy. The goal is to train neural ODEs for whatever you want to train them on, but using mixed precision. And what I mean by that and all that I will explain in a little bit. So neural ODEs is a type of continuous time learning approach, just if you haven't seen that. So for example, in supervised learning, you may have input features Y and output labels C. You want to map them with some DNN, but you don't just want to do any DNN here in F. You want to use something that is given by an ODE, or like a ResNet that has many, many layers. And that has nice interpretations on PDE and all of these different things that open up. They also have been used for generative modeling. So this is an example that I think popped up earlier also in Stan's talk, like an optimal transport type solver for matching two densities, where one may be only represented through samples. So this is common in continuous normalizing flows. You can have a conditional version of that. And that paper is actually one that came out of my stay here as a long visitor in IPAM, which was really great. And a conditional version of that, so since we are here at the SciML event, so in scientific machine learning, these techniques, like continuous time models, you can use them, for example, for conditional versions of OT. So here you see a bunch of OT problems that are all solved in parallel for different input data, learning conditional distributions from samples from adjoint distributions. And that clearly has many, many applications. Like think about the Bayesian inverse problems or any inverse problem where you can have coupled samples and you want to infer something. Those methods are quite powerful, and those can be formulated as continuous objects, and in this case, continuous or continuous normalizing flows. A similar example is an amortized control problem. So this is going also to the theme of like HJB equations, but think about parameterized versions of these that can depend. So where the controller needs to take new information into account. Those ones are basically solvers based on the method of characteristics for the HJB equation. And they all involve neural ODEs, and we could talk forever what's good about neural ODEs, but actually I want to talk about something that's bad about neural ODEs, because Stan also this morning discouraged us from computing characteristics, because he knows and everyone else knows that computing characteristics is expensive. So if possible, you should do smart things to avoid them, but when you can't avoid them, I want to give you a cheaper option than what you already have. Okay, so here's what we'll talk about. We'll talk a little bit about mixed precision in deep learning. I'm not so sure. I mean, I polled a few people this morning already. I would suppose, like my working assumptions is that numerical analysts usually like to work in double precision, or used to work in double precision. Now we all work in single precision, but not so much in half precision. And that's exactly where we want to go here, because that's where most of the nice speed-ups are in deep learning. And of course, machine learning engineers are already blazing the way. Think about DeepSeek, for example. We'll do something wild thing in 4-bit or 8-bit or whatever they do. So there's a big incentive to go there, and I'm going to give you like a little bit of a spiel why this could be interesting also for numerical analysts. Then I'll show you what people do in machine learning. I'll show you why that doesn't work for neural ODEs, how to fix that, and some nice applications. And this is all joint work with collaborators of mine. So Nicole is a now almost former postdoc of mine. She's moving to UTK. And then Elena and Brynjolf, who were visiting me last fall, helped quite a lot on the time integration side. Okay, so that's the plan. You can always interrupt me anytime, but otherwise I'll just keep going. Okay, so mixed precision training. What's the idea? The idea is to combine different floating point formats in algorithms. So you have some computation done in precision A and other in precision B. We'll only do 2 precisions today, but you can clearly extend this to many precisions. This is a very, very old idea. So if you look in early literature in linear systems, there's a method called iterative refinement. And the idea is that you have a low precision factorization of your matrix, but you use it over and over to match the performance of a high precision solve. So even like sort of before floating point standards came around, people were playing with these ideas, and now they are revived yet again in machine learning. So in deep learning, there is a clear motivation. So the models, the data, everything grows in size. We saw a talk about scaling laws, which is the new trend to scale everything up. But then when you do that, you have more compute and you have more memory bottlenecks in the training. The other thing in deep learning specifically is that the data and the training everything is very noisy. Also, when you think about neural ODEs, a neural ODE, it wasn't branded by us, but I think it deserves a special term, because unlike an ODE in physics, you don't actually care about the solution. You care about fitting your data. So you're not really married to getting everything right to machine epsilon in 64 bits. You're happy to make mistakes if they lead you to interesting places. So that's where it's actually very interesting to think about saving on precision. Rough timeline. So, oh yeah.
As you go towards the target.
Well, you assume. Well, we can chat a little bit about that. So the contrasting applications I have. So for supervised learning, for example, you don't care about anything. You just care about, is the final label correct or not correct. For generative model, and that's why I actually put these applications in generative model, you sort of care a little bit more. Sort of. You're more married to the ODE because you use that to approximate volume changes and other things, and that needs to be reliable. Maybe not. But okay. Anyway, there's a lot of room for error here, which we try to explore. And then rough timeline before 2017. For 2017, mostly everything was in FP32. Then there were these new GPUs out of NVIDIA, and they involved something called tensor cores. I learned more about hardware than I was thinking I should know, but okay, I'll share it. So there's like a new invention. So actually, when you work on 32-bit tensors in your favorite machine learning framework, and you use a recent GPU, your computation is not happening in float 32. They have these tensor cores, where inside of the tensor cores, stuff already happens in half precision by default. Shocking, right? But the world still goes on, and no one has noticed. Now I spoiled it for you. But anyway, so they have these fused multiply adds that are happening in a lower precision, but accumulate in higher precision, and so on. So there's lots of stuff happening. And now you have TPUs and NVIDIA, all of these hardware that exploits this. And there is a nice prize if you can make stuff work in 16-bit. So here's a typical way how machine learners tackle this problem when you actually want to train in low precision. We could also talk about quantization, but that we'll do after the poster session or so. But when you actually want to train in low precision to get faster, the way this is commonly done is you actually keep your weights in a high precision, but then when you compute a gradient, you try to cut as many corners as you like. So when you evaluate your loss, you cast everything to FP16, compute the loss, do the backprop, and then use that 16-bit, that rough estimate of the gradient, to update your weights in 32-bit. You have to keep them in 32-bit because otherwise you may ultimately lose everything because of small updates and so on. And that's sort of the established state-of-the-art in machine learning. So low precision arithmetic where it's sort of safe, like you think about big, or not safe, but where it's supposed to be safe, have like big matrices that you want to crunch, you try to do that in low precision. We'll talk about something called loss scaling. It's a very simple idea, but surprisingly needed and surprisingly effective sometimes, but not always, where basically you multiply your loss with a big number to get to the right range of floating points, because they don't all span the same range. Actually, I should show you this here. So there are different formats that you can think of, and they all vary between the allocation on mantissa and exponent. So you have more bits for the mantissa, gives you a lower machine epsilon, more for the exponent gives you a larger range. And sometimes you need to mitigate that, and there are all these dirty tricks around. But it's surprisingly easy actually to experiment with it. So if you have a code for any of these problems, you put something in PyTorch, for example, just put some command around, it's called autocast, and let it do his thing, and it'll do something in 16-bit. Your code will be 5.5x faster and eat half the memory. That's at least what people tell you when that goes, and sometimes it's actually true. Sometimes you actually do see some speed ups. Okay. So maybe for people who are more from a numerical analysis crowd, it's sometimes good to do a sanity check that not everything is totally new and out of the blue. So if you look at iterative refinement, you have similar constructs. So again, the goal is to solve AX equal B using low rank factorization of A, and or fast approximation rule, let's say, in FP16. And in that community, it's known, for example, that the residual has to be computed fairly accurately. So this is sort of my analog to the master copy of the weights in high precision, because otherwise the residual would essentially be underflowing to zero sooner than you may like. And also there, it's supposed to be, or it's important that you have scaling. So you would scale the residual up and down, because again, otherwise you would lose something. And there was, similar to now, this was mainly motivated by hardware. So you had these SIMD operators that you could use. But yeah, so all of these things sort of, I mean, and the residual, of course, in iterative refinement is similar to then the weights that you're, or the gradients that you're trying to approximate. Yeah. I want to take a step back. So this is sort of what people do in machine learning. Just put your AutoCast around and see how it goes. And of course, we tried that too, but then it didn't work. And then we went to the simplest possible problem. And I want to start with a very overly simple problem, or almost, then give you what we came up with, and then give you a more formal result of what accuracies you can expect, okay? So bear with me. So here again, like this is a Neural ODE. You have the following scenario. You have a state equation, you have some parameters, and you want to optimize for those parameters. So it's, you have to do two things. You have to solve the ODE in mixed precision, or as low precision as possible, but you really have to worry about also gradients later on. And why is this worth talking about? So you have many evaluations of F. You have a lot of memory because you need to store everything to do a backpropagation. And you have to worry about stability and other things that make ODEs. They have been making ODE an entertaining subject for centuries. And we want to tackle all of these. So let's first start with a very simple one. That's the model equation we start in every course with. So everything is scalar. My neural network weight is just a scalar theta that is multiplying the current state. And the naive, or the best approach would be this. There will be a few subscripts now floating around, and I'm throwing them at you. I'll explain them. So a sub L means low. So let's say you keep your U in a low precision, and you have an addition in a low precision, a multiplication in a low precision, and another multiplication here in a low precision. Okay, it's a bit clunky, but hopefully not too bad. And I think I'll use some color coding too to have different things. So that will be the ideal thing, because that will be lightning fast. But when you try to do that, then what happens is, so this is a simple problem. That's a simple problem, simple method. And you can study what happens as you increase the number of time steps and so on. And you see that in 32-bit, the blue one here is the orange one, ignore for a second, but this one converges nicely linearly as it should to the analytic solution. But what's interesting, when you go to 16-bit, what you see is actually the error associated with this method sort of at some point shoots up. Okay? And why would that be? I'll show you. But basically, at 16-bit, just in low precision, you cannot really solve this problem faithfully. You can only solve it up to a certain point, and then you have to be lucky enough to stop. This is not really what you want, because then the user may just pick a bad flag and have a relative error of 1 or something like that. And the very crude round of error analysis that fits on the slide would reveal why that's so. So whenever you round anything, you buy a relative error. So there's one here, the mu2, which is governed by evaluating all of these this product and getting that to 16-bit. And then the outer one here, this is associated with the addition. And then if you look at this for some time, you will realize that, okay, so this part here, this will only happen once per step, but additions, they will happen all the time. So if I have more n, more steps, then this will accumulate quite quickly. So the idea would be to keep that do that in a higher precision, so that this mu1 here becomes almost 0. Because this one is the one that would propagate as you keep integrating your ODE. And this is a fairly well-known thing in numerical analysis, that whenever you think about like a dot product, it's the same thing. You would want to accumulate this in a higher precision than you would actually compute. But for neural ODEs, it's actually quite attractive, because this blue stuff here, this will later on be the network evaluation. And that's oftentimes the expensive part. I'm happy to add something in a high precision. I'm happy to maybe save something in a high precision. That doesn't cost me much. And when you do that, then you stabilize the forward solve quite nicely, so that you have this orange dashed line that keeps going down as h goes to 0. Okay? So simple fix. And that's why you see a mixed precision. So you have a mix between addition in high and network evaluation in low. Okay? And I don't think there's a way to get just everything to low. So we shouldn't be too greedy. So now the next thing is you need to compute a gradient. So you implement this in PyTorch. You make sure that the precisions are mixed. And then, of course, you use the backward method. And hopefully that this would give you a reliable gradient. And for this equation, we can easily work out the gradient and see what happens. And again, we'll set h to 0 and hope that nothing bad happens. But when you use automatic differentiation, just for people who haven't done this in some time, automatic differentiation is, of course, saving us the day, we think. And what it would actually do is it would compute the gradient of, let's say, your last state with respect to theta by accumulating some changes that happen at every at every time step, and that depend on this new variable called a. And I call a for adjoint. So whether you use continuous or discrete adjoint, this thing floats around. And you have to solve it backward in time. And if you look at the equation, then this is actually what would happen when you use the backward method in PyTorch based on the documentation. It would compute a low precision approximation of A sub L by just reverting the computational graph and basically doing almost like a forward Euler backward in time. Okay? And there you may be already seeing a problem, because before I told you that the state you should keep in a high precision. But the backward, I found no other way that it would always map it to this precision. So when I use automatic differentiation on my mixed precision scheme from the previous slide, I see exactly the same problem shining through that I showed you before. So I decrease the step size, and my solution, basically my error, blows up. So what's the fix? The fix is do exactly what we said on the previous slide, keep this in high precision, and basically write your own custom backward, which we have done now, and hopefully reasonably well documented to be able to, so that everyone can use it. So what are the takeaways? So you want to integrate, whenever you want to integrate something, use a high precision. You can evaluate the network in low precision. Here, actually, it's interesting because I told you that the storage is expensive in neural ODEs, and you can see this here now because you needed these U sub, actually should be a U sub k, UL and superscript k. You needed to save all of these states. But now, since those ones only enter with a low precision, you can basically already slash your memory by a half, because that's a safe. To save in a lower precision. So you can quantize them. But yeah, we needed a customized backprop for that. And we're going to refer to this torch diffq package, which is very nice and very user-friendly for this. I'll show you some interesting failure modes. So it doesn't always fail in low precision, but we have enough evidence that it does fail, and it suffers from some of these issues. And we can also, if someone wants to pick me up on a fight later, we can talk about continuous adjoints, which I don't do, and in this case for a very good reason. Okay, but anyway, with this custom backprop, you fix this issue. So let's see what's left, or how it looks like. So in the forward path, that's what I told you. So whenever you have, so blue means the low precision. So the step function of your ODE solver, of course you can do many different ODE solvers, and F would be your neural network. So this you can safely do in a low precision, we think, as long as you keep, as long as you take the step and add it in a high precision. And that's, I think, a fairly sweet spot to be at. And then when you save these states, you do that in low precision to save some memory. And then in the backward pass, you do the same thing. So here the dynamics would be a Jacobian MATVEC, which here we actually recompute the step, I should say, to save even more memory. So we do this, we build the computational graph, and then we do an adjoint product here. And we do something that will be more evident later, so we may go back to the slide. I told you about this scaling of the loss function. I don't really like that. I have a shocking example why you would not want to do that in ODEs. So what we actually do here is that we always monitor the important scales and we adjust them as we solve the ODE, so that hopefully nothing bad happens. Okay. So here is a theorem that we have converging on different versions of the proof, but the result will always be of this shape. So we can show that the relative error of the states is sort of in the ballpark of. So it's bounded by something in the order of machine epsilon of the 16-bit. And the constants don't depend on h, I should say. So this is always the error you're going to get. And then the error from the accumulation, this one scales with 1 over h. And that is because basically 1 over h is like n. So you have n times this accumulation, and then, okay, this stuff is inevitable to grow. But these are the types of results that you can get here. For the adjoint, you get another term, which comes from the error that you make in the forward, which should make sense. But otherwise, it's the same thing. So you have the low precision epsilon enters without the dependence on h, and the high precision with. And the gradient is the same thing. So what this means then is, or how I think about it, is you can now make some choices and see how safe it is. So if you want to select, let's say, 32-bit and some h, so basically what you want is you want to make this term here go away, or be at least small enough to ignore it. Because you will never really solve, you will never really get below a relative error that is about the machine epsilon of the low precision anyway. That's the best you can hope for. So there are two ways to do this. You can choose the number of time steps small, so that h is large, or you can make the epsilon small enough. And we usually get away with 32-bit, but if that's really a bottleneck, you could go to 64. So the safe regime is where the step is much bigger than the machine epsilon or the square root of that. There's some danger zone. So when the h becomes too small, you may have to go to FP64. Not the end of the world for storage, but okay. And yeah, there's the expected coupling effect. But if you satisfy these rules, then you can save a little bit on your compute here, I think. Okay, so this slide shows you sort of how we envision you using this. I should zoom in. So in the end, in your code, all you do, so this is a code you already have, and then the thing you write is something humanly readable almost. So you say that when you are on a CUDA device, do something in 16-bit, and then we'll handle the rest. And yeah, then there are some failure modes. This ODE int is a famous method from the torch-dfq package that we shamelessly copied the name of. So when you load our package, the method should work. You will not notice the difference, except that some things work. And here are some cases, even for these simple problems, like a stable ODE system, where the blue, which is a torch-dfq, as you decrease the step size, oftentimes blows up. And the red solid is, again, our mixed precision implementation. So that always gets back to where you want to be. Okay. So let's talk a little bit about the loss scaling. because that one I've more or less swept under the rug. So this is like a standard maybe numerical analysis example. You're looking at the error of AX in high precision to this complicated expression that in infinite precision you would just make sure that it's 0, but math in numerics actually doesn't always satisfy all of these common sense rules. So this is one you can look at and how it depends on alpha. So what you can see here is that the error norm, basically when the alpha is too small, the relative error shoots, or the error shoots up. And why is that? Because basically you have underflows. So here you have underflows. If you make it larger, you're fine. I was smart enough to stop this early, because if you keep going for way too long, then you'll get overflows. But those ones you can easily detect. So you want to make sure that all your variables are in this sweet spot. And what machine learners do is they basically scale the loss by alpha, do a backprop, check if anything is infinite. If yes, shoot. But it's just a mini batch. Just throw the mini batch away, divide the alpha by 2, try again with the next mini batch. If you're good for a certain number of steps, you may double alpha and see if you can be more greedy. But what our problem here is that if you do loss scaling, what do? You actually only affect the terminal state of your adjoint. And you may think about scaling that up, making that really, really large, but you don't know what the ODE will do in between. So you may risk some overflow or underflow later on. So here's an example I cooked up to demonstrate this. So this is a simple ODE again, but this time we have a little bit more interesting dynamics. So this is time dependent, and there's a quadratic polynomial here that I cooked up so that the solution y covers basically the whole range of the FP16 system. So this is a log plot here, so you see these dashed lines. This is sort of the range of the normal numbers in 16-bit. And I made it kind of interesting enough to go through all of this range. And this is an example where when you take the terminal state and you make this large enough to not lose anything in between, then you basically shift this graph up. You have an upward translation of that graph, and then you'll get out of the range quite quickly. Or you shift it down, and then you'll have an underflow there. So this was one example where in 16-bit, when you do nothing, you can produce very large errors in the gradients, a relative error of 2000 or something like that. But when you do this dynamically, so you look at every adjoint step, you check the ranges, and you adapt accordingly and make sure of the bookkeeping, then you actually get pretty much the same accuracy that you get for the forward solve. Okay. Let's maybe look at one or two examples, and then happy to take questions and get some discussion going. So this is like a normalizing flow. Finally, Marcos will be happy. So this is a generative modeling problem. Here you see there's a special type of neural ODE. So you have some. This is the characteristics. This is a volume change, or approximating the log determinant, and of course we'll penalize some transport costs. And yeah, then we'll go for it, and we'll do training in 32-bit, 16-bit, and with our solver and torch-DVQ. Simple example. You see a couple of interesting things. So first of all, when you go from 32 to 16, you save a little bit of memory, not the 2x I promised, but this is a very small example. And it's also not so easy to measure these things. We save a lot of memory compared to torch-DVQ for reasons I don't fully understand, but one thing I do understand is that we are recomputing the graph and they are storing the graph, so give us that. But we pay for that with a little bit more compute time. And the annoying thing here, if you look at this, the motivation was to actually save time, right? Or we spent more time. And now you can think about, okay, so this is an artifact of a bigger, it's too small of a problem for sure, but also we learned that not every problem size is good. So bigger is not always better. You have to be very careful with few choices, and unfortunately in this business, you have limited control because your data comes in a certain dimension, You have no control over that, and then there's not so much compute. So we tried very hard to cook that up. But before I show you what we've done with speedups, here one question we had, okay, so this is a nice example, everything worked. So you don't see no difference between any of these loss curves. This is exactly what you want. You want to use low precision. You don't have high hopes to do better than high precision. You just want to, like, it's a typical numerical analysis problem. It's not very sexy, but when you leave your job and nothing blew up, then you're happy. Okay, so this was good. So now we wanted to make it be a bit more adversarial and see if we can make the torch DFQ actually blow up. And so we were able to. And of course, the solution was you add more time steps. So if you add enough time steps, then you have these densities that with a torch DFQ, sort of at some point it loses it. Even here, like the usual setting that I have is n equal to 16. So you have to go like really high, and then at some point you can produce some interesting failures. Although we learned now that for this one, you can actually, with loss scaling, most of the time be happy, but not always. And the idea was to be always happy. Okay, so this is a toy problem. We're having larger problems in the making. But I did make one problem from much earlier on. So this is like not a generative modeling problem, it's a classification problem. And there, many years ago, we worked on CNNs. And the reason I like to use this one is, so this one is a CNN. So W is a convolution matrix, B is a bias, N is some normalization, not batch norm, but instance norm, and sigma is some nonlinearity. And if it's cooked up this way, it's almost like a ResNet, but in a ResNet, you would actually not call this negative W transpose. You would have this V and then be separate weights. The benefit here is that here you can actually have some notion of stability. So some contraction. It's almost like a gradient flow. Okay, so we used to like this one, and I got it out of the basement to not give any excuses to unstable systems. So here I used a very small data set. So you have 5,000 training images, 7,000 test images. This is a subset of ImageNet. You have to imagine that this ODE is only part of the network. I made sure it's the biggest part. So you have 3 of those blocks. And then you have some convolutions in between that do upsample, downsample, channels, all of these managements. And this one was relatively, is known to be relatively difficult to train by now. And I did a few experiments. So again, torch DFQ in our package with all of the different options. So I have two 32 bits here. So this is float 32, like real float 32. You can tell NVIDIA to not do any shortcuts, and that kind of became interested in experimenting with that. This is the normal float 32 that you have, then the B float, and then for 16 bits you have to do all of these scaling options. And there the torch DFQ actually failed at least twice. And it failed even with the gradient scaler, which was interesting. So let me show you that. So I know there's a lot going on. So basically you have the 32 bits, and this is sort of what you want to beat. So this training accuracy. I don't want you to look too much at test accuracy because that's like more wishful thinking and luck involved in that. But this is sort of the optimization. So if you have poor gradients, then you will not be able to fit your data as well. And yeah, then you see mostly that if you go from the real float 32 to the one that NVIDIA does by default, you get more or less the same. If you go to the B float, you pay a little bit more of a price. And then the interesting part is if you go to the IEEE float 16-bit, then torch DFQ fails in both cases here on this one. And yeah, we sort of save the day in the end. And then you can ask here about, so here you actually have some time benefits. So the torch DFQ in 32-bit is like 0.36. And it does get much faster here at B float 16. And the secret to do this is to make the network have the right number of channels. they must be divisible either by 8 or 16. And that has to do with the way these tensor cores are organizing the memory. You have almost no hope to find out that you have fit the right size unless you do a plot where you make the network bigger and bigger and you monitor the runtime, and then you see the runtime goes up mostly and then has a delta drop where you've hit it. But anyway, so that's a little bit of engineering. Okay, so what did we look at? We looked at mixed precision training. I would say it could be done more in our community because that's where all the hardware is headed, and it's like if you do it carefully, you may have big advantages. Actually, in this one, I should highlight. So here you have an example where you go from 8 gig of memory that you need down to 2 gig. That could be interesting when you think about now you could make the network even wider and so on. And you want to not spend too much money on buying more GPUs, where this would become interesting. Or I know that a few people here work on transformers with neural ODEs. That seems to be like the ideal test bed, because there you have a lot of memory problems, my guess would be. Yeah, so anyway, reducing the precision is an easy knob to turn when you do it carefully. There, I think, was a gap that will be filled with our paper, where it was not so clear how to make the backprop work without rewriting it, which is what we did, but that's now done. Because the standard sort of whitelisting and blacklisting of operators just doesn't make this stable enough. And yeah, then we have some first results where basically the 16-bit saves the day when you do this scaling and when you do the mixing of the precisions accurately. And we have some theory why that is the case. And yeah, I would say that it's always more robust to do this. It's always more memory efficient. And sometimes if you're lucky, you may even be faster. Cool. Anyway, with that, I'm happy to take a few questions. And then I think we'll have a very important announcement also by Wenji.
Yeah,